So I will follow Linda with what is the sort of models we have to do single path sigma and how we could use them as they stand, and then point out some of the limitations as to the way that we're parameterizing the problem. Most of this will be showing you a little more detail on the Lin et al. Study, and as I said, person Lin is here, so as well as Melanie and Brian and me, and who else was on that? So surprisingly, a lot of the authors of this paper are here today. So we'll talk about the Lin et al. Proponent model, and then some work that Manuela and I had been doing in the last year, looking at the California data, focusing on the longer periods because we wanted to compare with the ability of simulations, the cybersec simulations, to capture this effect, but that will also be extended to the shorter periods, somewhat of what Linda was showing. So Lin, the paper is, or their data sets in distance and magnitude, it's mainly magnitude 4s to 6 is dominating the problem. We left out the Chi-Chi earthquake in this analysis because we were trying to figure out how to describe the path from an extended source. The rest of these were small enough that we just simply used the hypocenter to describe the source. And then we're looking at these earthquakes here and the stations. So what we were just talking about, most of the stations are on this side. So we may be having a more limited paths that is sampling this part more than it's sampling the other paths through the island. The data set, we restricted it to with at least 10 or more recordings per site. So we didn't have to go down to 3 because they had so many earthquakes from the Chi-Chi aftershock sequence, and some of them were up to almost 40 stations or recordings per that station. So back to this picture here. So Linda was showing you this closeness index and this standard deviation of these deltas. This is the reduction, it's a scale factor on the phi SS. Okay, so that's how you should interpret what this number is. We've already taken out the site term, so we've gone from phis to phi SS's, and then this is now set so that if there was no path effect, everything should be near 1. That means there's no systematic path terms that we can pull out. So then when we extrapolate this to small numbers, like here around 0.6, we would say if you took your phi SS and multiplied by 0.6, that would be our estimate of our phi SPD, this single path phi value. So that's how we're using this. The reason for doing this was to avoid having to put earthquakes and sites into bins, okay? So that, because that's always gives you trouble, what's your bin size and how do you do that problem? So this was at least a continuous way to merge all the data together, but it does miss out the effects of different distances, and azimuths are gone. It's one simple way of doing the problem. So this is the same kind of pictures just for different periods, from short periods here to longer periods. You can see what these slopes are. It's, the same basic data is available. This is kind of what our model looked like here. Looking at numbers from around 0.5 at different periods. This is the shorter period. To longer periods, seeing the path effects only to about down to 0.7. So what we're really seeing is the path effects show up more at the short periods than they do at the long periods. It's kind of opposite, back to what our thinking had been, that the long periods would have a more repeatable effect and the short periods would be more difficult to pick up these kinds of features. Same thing happens with the source, so we actually have a regionalization of tau. I'm not going to focus on that, but there's a repeatable reduction in tau here, the same kind of a thing of about 25% if you have an area where the sources are continually firing off. That might be from more similar stress drops, or a systematic variation stress drop, or it could just be radiation pattern. The orientation of the events would be repeated. We don't see a period dependence of this thing, and so but there is a reduction in the variability of our WB, our delta B terms, when we look at them grouped by area. So our standard deviations look like this. So for PGA, the Lin et al. Study, if we looked at a total standard deviation, it's 0.73. The sigma SS is 0.62. So I think Yusuf was asking this reduction here, or he asked for the fees, and I gave him this number instead. I'll show you the fee reduction later. The sigma SP, so the single pass values are much lower. So this is a large reduction. It's almost just over a 50% reduction of the original standard deviation, or under that. If we look at other studies, so Gail Atkinson did some of the first work on this, just looking at a small area in Southern California, and found similar reductions here, 0.71 to 0.62 down to 0.41. And in Japan, Moriwaki did the same thing. He didn't bother with this intermediate step. He jumped straight to this standard deviation, but we're also getting a similar value here, somewhere around 0.4 natural log unit, compared to these numbers here. These have different magnitudes in them, but they're generally sort of magnitude 4 to 6 data sets to get enough data. So if we looked at what would be in Lin's model of this, so this becomes sort of one of the proponent models for how you would deal with this, are phi SS's. So Yusuf, this is the comparison of these numbers for Taiwan, not for California, and we need to repeat those. So the phi SS's are around here 0.4 to 0.5. The single path ones are around 0.25 or so to 0.3. So it's not quite, so as we said before, this reduction, that's about a 40% reduction. That was from those other curves I showed you at the shorter periods, and the reduction is less, maybe a 30% reduction at the longer periods. Okay? If you went, so this is, I think, the way that the model should be used, is looking at the difference between these two. Part of the reason for that is when we go to sigma, look at, here's our sigmas in this 0.6 to 0.7 sort of range, our sigma SS's are reduced, and then our sigma SP's are here around 0.4. This reduction from this value, if we go all the way back to this, or even sigma, here, we're looking at the impacts of the site-to-site variability, and that may change from region to region. So Taiwan might be more similar than California or Japan. So I think that's, while I'm going to show you numbers before we were normalizing by this term, I don't think that's a good way to do the problem if we're trying to bring in global information and transport that to California. But so this sort of gives you the impacts that we're talking about. And these are big numbers. This is an important difference in the hazard. This will really change the slope of the hazard curve. Standard deviations matter, and when we change them this much, we get much steeper hazard curves, but our median has to adjust also. The total hazard at 10 to the minus 4 could be higher, even using this steeper or smaller standard deviation, if the median at your site is above average. Because some sites will be above average, and some sites will be below average. And so you need to figure out where your site is, and then the uncertainty in that process. The difference between these two is really telling us how much systematic and knowable features in the site and path terms have been just lumped into an unexplainable randomness term in standard analysis, right? And so this is where we want to be heading to be able to understand things, but properly capturing the limitations of the available data today, which will broaden this out as we add the epistemic uncertainty. So if I had no information at my site, I could still say this is a number of 0.4, but now I need to add in a very large epistemic uncertainty to get me back to this total value. All right. If we try to look at these ratios that I just said not to do, but this is the way that we've summarized them previously. Okay, so these are the ratios with respect to the total standard deviation. So from Lin's paper study, it's around 0.5 to 0.6. For Atkinson, it's more about 2/3, that magic 2/3 number that shows up in earthquake engineering all the time. And then in Japan, it's more like lower, like 0.4 to 1/2. So I think this greater reduction is because of the larger differences between sites in Japan than we have for example, in Taiwan or in California. So that's why this is probably not the right way to try to parameterize this problem and move it around. I think sticking with the phi-SS's and the phi-SP's is the right way to do it. So the other approach study, this is by Manuela Villani, and I have done this just recently. She had taken the NJ West 2 data set that we're using the ASK13 model. This was all of the data, and then she took only those data in Southern California with at least 5 recordings per earthquake so that we could get the event term, okay? And then she started to do the same kind of an analysis. So it's very similar to what Linda showed you. These are the stations shown by the triangles, and the circles are the earthquakes. Not every station has a recording from each earthquake. Most of them are small in the magnitude 3 to 4 range, but we have some larger ones in there as well. Then she also looked at the cybershake simulations. Those are different magnitude range, so 6.5 to 8, so bigger earthquakes. We treated them essentially similar to the empirical data set. There's like 400,000 data points per site. Okay, so there's a huge number of data to work with. But she went through that and evaluated the site and the path terms, and then we're seeing, are these similar to what is observed empirically? So this is one example of essentially getting a fit, of an empirical fit to the full data set. And then this would be one site. So this is site 18 for a magnitude 6.5 earthquakes and for a magnitude 8. Our average model is, our data are here. These are showing GMPEs, and then the line through here is the fit. These are GMPs down here. This line on the top is the fit that she had to the full data sets. And so then from that, she went through and estimated a site term for each of the sites. And this is at a period of 3 seconds because the cybershake runs are for longer periods. So on the bottom is our empirical site terms, and on the top is the site terms from cybershake. The stations are not co-located always, but they're within several kilometers of each other. So there is some, if you are moving from a basin onto a rock, we'd have a bit of a problem, but we had to do something to be able to compare them. And we at least get a positive correlation, so that's encouraging. Okay, that where empirically we see higher than average, so 0 would be average. This is above average long period motion. Then the simulations are also predicting above average long period motions. Then we also looked at it for path effects, and I'm going to just show you in sort of this format here of the same closeness index. The Lin model is shown here for 3 seconds, so remember that came down to around 0.7 at really short periods or short distances. The empirical data are shown here, so it's a similar type of a decay. It's actually a little bit lower, meaning here we're getting a more reproducible path effect in Southern California than in the Taiwan data. And then the simulations are shown by the blue dots here. And so those are showing very repeatable effects for these larger events. And whether that's too repeatable or not is the issue that we're facing. But this tells you, if you believe the simulations, you could be getting down to a number maybe of a half of what the standard deviation is. Remember, this scales the phi-SS term, right? So you start with phi, you remove the sites so that you're at phi-SS. Now what happens if you knew the path, how much could this come down by? So where are we and what are the limitations? Yes?
Is cyber 3D or 1D?
3D. That's the whole point. It's the 3D modeling of Southern California, okay, to capture all of the glory of their 3D structure. So when we compared this, I wasn't going to go through it here. When we compared it on a location by locations thing, we found some sites that were highly correlated between the path effects from the empirical data and the simulations, and other places that it was actually zero or negatively correlated, meaning they were going in the opposite direction. I think it tells you there's promise here, but it really needs improvement in the 3D model before that's ready to go. So in summary here, if you're going to try to take a global PSP, how should you be doing it? Our problem is if we take the numbers just as 0.25 or 0.3 from Taiwan, can I translate those to California? These effects really may be more systematic from one region to another, and so we need to be careful about doing that. The normalization approach we had done before, relative to a total standard deviation, is probably not a good way to do the problem. We have these might not be, the site variability may differ from region to region by a large amount. I think the right normalization, if you're going to do it, is the phi single path phi over the phi single station. We know how to do this pretty well. What Linda showed you is that these numbers are actually more stable from GMPE to GMPE than just the total standard deviation. And I think this will, for within a region, is probably a number that might be better extrapolated from Taiwan to California or from Japan to California is the way to go. Manuela's model here only had looked at 3 seconds. She's going to go back and just rerun the whole thing with the shorter periods to see how we're coming up with those values, and that gives us something to compare with as well with these global normalizations of those two numbers, but that work isn't completed yet. All right, any questions? Adrian.
Adrian Rodriguez from Virginia Tech. In the closeness index plots, it seems that the functional form that you select for the extrapolation to a closeness index of 0 would have a significant effect. Why did you choose some functional form rather than just choose the value at the lowest closeness index? Because you could select other functional forms that fit the data and extrapolate differently.
Okay, so almost if we go way back to these things, well, probably written this. How steep this could come here and then go crashing down, or right. We were just picking a smooth form and then saying, how can we get down here? That's sort of our idealized path effect, but I think you're right. We could say stop it at, come here and just go flat and never drop below that value. That's probably a good way to do it.
I have a student who worked on the Tohoku aftershock data using a gridded approach where we're looking at attenuation terms on grids, looking at the percentage of a source to site path that goes through a grid. That's similar to tomography approach that they do a lot in seismology. And that way you can get directly path terms because you can integrate across your regionalized attenuation. The good thing is that we get almost the same single path fees that you get. We go down to period dependent, but center around 0.38,
okay.
0.4.
So what you're saying is you have enough combinations that you can do. Here's a bin, a gridded sources for this site, and then you can do it. So if you had the right amount, enough data, clearly that's a preferred approach because then it maps out that whole effect. This closeness index was a way to try to say we don't have everything sampled, how can we generalize it? Again, this is a topic that moving forward probably could be some other way of parameterizing it. I think this has worked remarkably well considering what we were doing when we came up with this idea. Brian is shaking his head because this was part of what he came up with. But it's really, if you have enough data, you can do exactly what you said. I think most of the time in the areas we're going to be looking at here, we're going to have to do something to help us extrapolate and to fill in the holes. Other questions or comments? Doug or Bob? Jennifer? Okay.
Gabriel, following up on Adrian's comment, another As I think you have mentioned, the problem with the binding or tomography approach is that you have to choose a cell size, which involves some compromises.
Right.
Another way, and I can see how you do it for Q, as it was done by Phillips. I'm not entirely sure how you do it for the geometrical effect, but it would be to think of attenuation, and I put it in quotes, as a two-dimensional random function for which you have sampled along certain paths and no more. For which you have sampled the combined effect along certain paths.
Right. So for this project, and we need to talk about sigmas, and so let's start with the most complicated, so the path part. Our use of that would be just for Arizona, for the California sites, or California events. So this would not be used for the local sites, because we don't have that, or local sources, we don't have that information. And for Diablo Canyon, we don't have enough information yet to start to constrain the path effects. The data, the sort of additional instrumentation Marcia talked about will start to help us to do that, but that is probably is a years-long data collection effort to get to that point. So one issue to talk about is this the right thing to do for those sources on the California earthquakes at Palo Verde? Including it in this framework that we have what is a knowable, potentially knowable path effect. We'll have some data to help us to constrain that to get with our 5 or 6 events that we've got in the southern end, and maybe there's 10 or more up in the northern end of California for that particular ray path. Now because of the small number, we have to broaden that out in its uncertainty. But are there comments or concerns about the formulation that we're using?
Actually, one good thing there is that you get more data for those particular paths, because it's from the more active regions.
Correct.
That's a nice thing about it.
That is what's good about this in general, is that we're sampling the more active sources. So overall, these would be the things you would expect to control your hazard. So the most relevant sources are getting the most accurate model. The less relevant ones because they're lower activity, will have less impact on the hazard, and we're not modeling them as accurately. For a lot of those, the only way out of this in the long term is to get a good 3D structure model and be nice to be able to run lots of simulations and get a similar answer from your 3D simulation models. That's probably in the next decade is where we're going. Okay, Adrian.
You're not using data in Palo Verde to constrain the patterns, correct? Because
At Palo Verde itself, no, but we have nearby. So I think the closest station is which one? There's one pretty nearby, right? But we have data from that. The closest station for which we have data, or site, was I think 5 kilometers away, approximately.
Because one concern, and apparently it doesn't apply here, would be if you are trying to constrain your pattern, most of your earthquakes are coming from one region, as Gabe indicates, but you're also using the same data to constrain your site term, then it will be difficult to uncorrelate both. If you're
Oh, sure. If you only had it from one path, you couldn't tell if it was a path effect or a site effect. You're right. So for Palo Verde, the site term will be based on geotechnical modeling. You're all so quiet. I need to bring Nico back up here. Yes, with making these maps for the SOMS maps for path effects, and we'll see what that looks like. Christine.
Okay, since you complained, I'm gonna talk. I'm trying to stay quiet here because this is not my workshop. But a general thing, I think we need as a community to look at is all those site-to-site effects, how they correlate with geotechnical models. Because the site-to-site effects, the phi S2S, as Adrian said, some of it comes from way deeper, and then it incorporates also maybe a kappa terms that we don't separate. And we'll need, as a group, eventually to get to that answer, because I think we might be missing something in the way we compute our standard deviations in the end, and we might assume some repeatable effects. And I know, Adrian, you're going to look at nonlinearity, but that's something that puzzles me a lot, because if we get our repeatable side effects from small events where everything is linear, and what is the impact on nonlinearity on that?
But
So
that's,
that's
but
a
our-
bigger question.
But the intent of the site term is the linear part of the model.
Okay.
It's not constraining the nonlinear part of the model, and that has to be propagated through with geotechnical models or something else, right?
But still, how are you going to combine those, and which part is actually included?
I think
It's a
what,
bigger question.
right, but what Adrian brought up is if you're doing a geotechnical model approach and you took this empirical reduction from phi to phi SS, you are taking, empirically we get everything in there, right? Not just the shallow part, but we also have the deeper part. And you may not be allowed to take full credit for that reduction to say, well, I've done a geotechnical model, now here I've got it all in there.
I agree, and that's the point, but we'll have to look at that systematically to see.
Which is
what
why
we-
when we have data, we prefer data, right? Because it's got everything in it, and I don't have to say I only have the top 50 meters or 100 meters model, then I'm not sure what's happening below. But the framework, are there any, I think most of you have seen this or the basic structure of what we're trying to do. This is the way ground motion models are going to be moving. If we're using global models and they're ergodic, you really limit the accuracy that you can make those models work. Right? Because you're now saying everywhere in the world is the same. Okay? And that's clearly not the case. In fact, it can be very different. And as we move forward, this is the big change that's going to happen. We're starting that, and we're at least setting up the right framework to take this, to move this forward with potentially large epistemic uncertainties now as we're setting up the problem, and then having a structure that allows you to take advantage of data as you collect it and reduce the uncertainties and adjust the medians up and down as your data is telling you, no, it's higher in this period range or it's lower in that period range. But are there any general comments on that, Bob?
Bob Budnitz from the Diablo Canyon Independent Safety Committee. If I accept your formalism as the way you want to structure this analysis, is there, how would you structure a data collection effort if you had, let's just pretend, 3 or 5 or 10 years in the future, to optimize what you'd collect to support this best? You
So-
talked about the next year, but I was just thinking, gee, we're not going to have better data in 10 years unless we collect it, and
Correct.
we need to deploy it in a way that supports the models that we think are
Correct.
the best approach.
So what do we need to be able to use these data? It's
Yes.
not individual, it's not just a bunch of recordings at my site.
No, in fact, it's exactly way more
Right.
than that.
Because I need data at my site, but I also need data around so that I can take out the average source effect. Otherwise, if I have just a recording at my site, one of them, I don't know if the source was unusually high or low, or the wave propagation was different, or the side effect was different. So I need enough recordings, ideally as mutually distributed around the source, to be able to pull the source term out. So in Arizona, we would be using the California data and the Arizona data to remove the average source term. Was that earthquake more energetic or not? So you need that.
But it's easier in Palo Verde in a way than it is at Diablo.
Diablo Canyon, what we need to do is we're probably going to have to install a few additional accelerometers, so probably in the area of trying to move in sort of maybe 5-kilometer step sizes or something like that in a bit more dense array, so that we can take advantage of the smaller earthquakes. And that's where we've started that, and what Marcia showed you about getting some stuff offshore, as well as starting to put instruments onshore, will lead to that. But where we're going to get data in the next 10 years is going to mainly be magnitude 3s, right? It's not going to be a whole bunch of magnitude 6s. So we need to have the density of stations and have them, sensitive enough and in a quiet enough area. That was part of our trouble with our current site, so that we can record these small ones and take advantage of them. But for the site term, I got to have something on the same geologic unit and ideally pretty close to the power plant. So that's a tougher one to get at, but I think we can pull out these other pieces as we move forward. Does that answer your question?
Yes, it did. I was just, it then leads, it doesn't beg the question, it goes straight to the question about whether soon you'll have a specific recommendation about where to deploy. And
Yes,
what.
so
It goes straight to that question.
right. So part of what as you know, part of what I do at Diablo Canyon is to try to say, where do we want to be in 10 years and what do we need to do to be doing a better job of this whole thing? And I think this is the key moving forward. This is the big change in ground motion models, but you have to have certain data available to be able to take advantage of it. And so we are looking at that type of a problem right now. Already our improved broadband network, which is getting us sort of 50 kilometers around, helps quite a bit as well. But we need to get a little more densely spaced accelerometers.
But no, as you know, deploying for the 10-year picture is essential, but of course, 2 or 3 years hence, it's going to be it will have already gathered a third of that information,
Mm-hmm.
right?
Right, you can get started. And so
Well, you have to get started.
the advantage of this framework is it allows you to incrementally bring in information. You don't have to have everything. You would just adjust medians and epistemic uncertainties as I go from 2 recordings to 5 to 10. I will start to tighten my uncertainty band.
Yeah, and if we have a formal process for updating, I mean, the Bayesian formulation provides that, then at any time you can do that updating and see where you are.
Yeah. Okay, I think there was a comment here. Ralph, hang on. Wait for the microphone.
Maybe I didn't understand, well, I know I didn't understand most of this, but I mean, if you wanted to check to see whether or not this is really going to work, I mean, why wouldn't you choose a site, it doesn't have to be Diablo or Palos Verdes, but I mean, just choose a site which has a good number of recordings with small earthquakes and big earthquakes, stiff site, and see whether or not you really get the reduction that you expect.
We do. So that we've done. So maybe I didn't make that all clear. This is doing that. So now I've got not a couple of recordings, but say 20 recordings in these sites. And that's where we see going from here to there is the change. So we've done that and we know that it works. Now the problem is how do you move that to a site that has a small amount of data, okay, as opposed to 20 recordings. So I think up here I get to be as a proponent, I say we've already done that, okay? And we've demonstrated we can see a systematic reduction. Okay? This isn't statistical differences, this is robust.
So as you go to, let's say, Diablo Canyon or Palos Verdes, are you expecting something different?
That is our fundamental question. Now, how do we say this works? So you told me go to where I have data. I've done that. I've demonstrated this effect, right? So we know that the conceptual model works. How do I now borrow strength, right, or transfer that information from where I have it to a region that has less data? For Palo Verde, right now we're going to have on the order of, let's say, 15 recordings, or I think there's 15 to 20 earthquakes that we're using to be able to look at it in the region. It's not right at Palo Verde, so we don't get to the site term, but we can pick up the path term. We'll probably split those into 2 groups, so we might have, I think, the southern groups through the Salton Trough might have 5 earthquakes, and the northern path might have 10. Okay, and so we'll apply that, but now because of fewer events through the Salton Trough, it's greater uncertainty in our estimation and constraint on that path effect. But we're set so that when we come back in 3 years or 5 years and I have more events, I can now tighten that up. It might not tighten around the center, right? It might collapse at the top end of the range or the low end of the range. But this gives you a framework for moving forward and incorporating information in a systematic way. Is that answering your
Yes,
question?
it does. Thanks.
Okay.
So, just in this seismological community.
Can you put that a little closer to you?
Of course, what you're doing has been done for decades in terms of calibrating stations to calculate magnitude.
Right.
So at the bottom of all these regressions, we assume the magnitude's known, by the way, which, of course, it's been calculated from a bunch of seismograms,
Yeah.
which are an average of quantities like this. They're just highly damped response spectra, not lightly damped response spectra. And we've known forever that you want to put in some sort of station static
Right.
in order to give you a more
and
stable
sometimes
solution.
So at Berkeley, we would have station corrections from, the Tonga Trench and a different set of station corrections from a different area, right? And that's all this is.
Yeah, that's right. And so the statistics out there are been known for a long time. You get, sort of decrease your variance by 30% or
Sure,
something like
but-
that. I mean,
But in the seismology world, they would have hundreds or thousands of data,
Totally.
right? And we're at a smaller number, but it's the same concept.
But I said this before, I mean, so this is gonna help us reduce our variances, match most of the data, but when we get out to the extremes, we've all seen these stories like San Fernando, shattered ridge tops, out in Hector, bombs moved, by tens of centimeters, and we've never recorded these motions, as far as I know. I on the top of the Loma Prieta, all the redwood trees had their tops snapped off.
But-
I've never seen anybody come up with a ground motion that does that. And so we see these things and we're questioning, will what we're doing capture those kinds of phenomena that we occasionally see?
Right, but we do have ground motion data that are really high, and that previously people would throw out as being anomalous. And we've stopped that approach in this business. Big ground motions happen sometimes.
So, just
Right.
curiously, what is the 100,000 year Diablo peak acceleration number?
10,000 is about 0.8 G, and
0.8 G.
100,000 would be, you would take cube root of 10 times that. So a little more than about 1.8 G, something like that. That felt like an orals question.
Curves, and at the end of the day, all of us have to look back and see,
Yeah.
does it make a
Right,
connection?
does it make sense? Sure,
Yeah, yeah.
sure. I agree, and appreciate your comments, because you're telling us, let's do the checks, is this all making sense? And what other analyses can we do? I think, following up on what you said, Tom, you didn't say it as explicitly, but once we reduce this and get smaller distributions, there's probably a greater chance that it's going to deviate from log normal as opposed to these broader distributions. So that really needs to be carefully looked at, right? Because now just a little bit of a bump becomes a large mass compared to before, where we were already so broad we kind of got out there. Any other comments? So, general agreement that single path is the way to go. We're not going to be there. What about, are there any discussions on the single site approach? So what Linda showed has this fairly robust, I would say, evaluation of that term. And an advantage of that approach is it is less variable around the world than the regular ergodic sigmas are, which helps us to try to be able to borrow strength again. How can we move information for where we have lots of data and believe that it's applicable? This is key for the East, especially for what Christine is worried about. How robust and stable are those standard deviations?